just kind of giving you a taste of what things to expect, what things might be coming on the horizon, and it's also a chance for you to give us some feedback because the folks that you've heard talking today have some influence on, kind of the direction of some of the software packages that you're viewing. So if you see something that's interesting or you have other ideas, we'd like to hear about that too. If there's something particular that's not being met on the systems today, that would be interesting to us. But I'm just going to kind of go through and touch on a few things that may be interesting coming down the road. So why is I/O changing? So of course applications are changing for one thing. We're getting more problem domains on the systems than we ever had before, and as a result we're seeing more techniques used to process data. There's increasing emphasis on sort of workflow-oriented jobs and different programming models besides just normal MPI. And of course the systems themselves are changing. The big one that we're looking forward to at Argonne is the Aurora system, which should be around in 2019, and it's going to have memory on storage on each node in the form of non-volatile RAM, stuff that's not exactly on the market yet, but we trust will be there by 2019. It'll also have more conventional burst buffers, so nodes set aside where you can reserve space, sort of like we saw on the NERSC Corey example earlier today. And of course the network will be totally different by then, and taking on some new technologies. So what do we need to do as a result? First of all, the I/O libraries that we've talked about today, we're going to have to update them. Things like HDF5 and NetCDF in particular, the data formats and the compatibility and the sort of ecosystem that's built up around them is very important. We're going to keep using those things, but we need to update them to work effectively on the new systems that are coming. So to give an idea of what kind of things might happen, first of all, the optimizations that are implemented in these libraries, particularly at the MPIO level, will need to be updated to account for the new hardware we have. The storage devices, especially non-volatile memory that's directly attached onto your compute network, is going to be a lot faster and a lot lower latency than these kind of old style file systems that we've had. So that's going to shift the emphasis on optimization strategies in the libraries to take advantage of that. There's also a lot of things that we can do in these libraries with intermediate storage, your burst buffer, or some other staging area that you have in addition to your file system. So as an example, since you're going to be writing to an intermediate region and then copying the data out to long-term storage, that means there's a window there to change the organization of the data because you're making a copy of it anyway. So for example, when you're writing a checkpoint, the data can be organized in a way that makes it fastest to write without any regard to how you're going to do analysis later. And then as you're copying out to the file systems, you reorganize it and put it back in the normal order so that tools will work, that sort of thing. And you can do other transforms in the data on its way through. So this might be a good chance to do compression. Compression is usually hard to do in parallel in a library because if a lot of parts of the data are being compressed independently, then you don't know how big they're going to be and it's hard to lay out the file properly. But if you have an intermediate area to do your compression on and then you can fix the layout later, then that solves part of that problem. So we'll probably start to see more of these transforms, either changing the organization of the data or compressing it, or even doing some limited analysis on the data on its way through is going to be more common in the future. The next thing I want to talk about is new data services. So everything we've talked about today has been oriented around file systems. You have directories, you have files, you've probably layered some data models on top of it, but when you get down far enough, it's just a file. But that doesn't have to be the way things are. Instead of just having one file system and everyone uses it, maybe we have customized data services that are more tailored to individual applications. And some of this is inspired by what you see in sort of the big data and cloud computing area. So people are using Hadoop, they're using Cassandra objects, they're using S3 storage. And the reality is in a major HPC facility, it's not practical to stand up servers for all these different flavors of things you might want to do. But you could imagine that we kind of dynamically on demand, when someone needs something, launch services that'll do that particular data model for them. So we're thinking about ways to make data services that are a little more customized, not necessarily long-running, but something that can just be brought up to serve what you need to do. And really, apologize, the labels are kind of missing on the top of this graph, but this is already happening. So there's software packages that you can use now. Data Warp is really one of them. Data Warp is kind of like a temporary service that just comes up to run a little file system for your scratch area. There's things like FTI and SCR that do checkpoint management, can do redundancy calculations, parity calculations, that sort of thing. There are some distributed key value stores that you can run on HPC systems now. There's libraries that can do, systems that can do library management, dynamic loading. And these are all things that aren't something you run a dedicated server on. There's something that you launch with your application, either within your application or on some dedicated cores to do the specific thing that you want done. Well, these tools are all good. The thing that we see in the future, though, is a little more convergence on how they're built. In particular, maybe we can build the building block pieces of the storage system so that when we have 6 different data services that we want to run on the system, they all share the same network transport, the same access to storage, and we get a little more portability and reusability out of these. So that's something that we're likely to see in the near future, is sort of a more microservice model for storage. And talk a little bit about instrumentation. So Darshan has been pretty successful, and we've had a lot of success stories where we've made an application go faster, but we're not quite getting everything out of it that we'd like to, and we have a lot of ideas for how to make it better. So the first thing is just to expand coverage, make it work for more applications. So one thing is that we could instrument more libraries than we do now. Right now it covers POSIX calls, MPIO, and a little bit of NetCDF and HDF. But what we're doing is going to a modular setup where you can add modules, maybe even system-specific modules that collect extra information. And what we've done so far is there's a module that will collect Lustre-specific information. It can tell you more about how Lustre was behaving while your job was running. We have modules that will collect BlueJeans system information, so you can find out a little more about your topology that you had while your job was running. We've got modules that will capture standard I/O, and in the future we're going to expand the HDF and NetCDF coverage so that when you look at that initial PDF that shows you what happened, you'll get side by side with all your other things, a summary of how fast was it at the HDF5 level, how fast was it at the MPIO level, how fast was it at the POSIX level. And this modular setup is kind of organized so that if you're not using a module, it doesn't hurt anything. It doesn't turn on unless it sees the interface being used. So there's a separate little piece of the library that's responsible for looking at these things. If it collects data, then when Darshan shuts down, it gets stored into its own portion of the log file. The log file is going to be self-describing so that if someone adds a new module, create a new I/O library, the Game of Life I/O library, and you want to instrument it, you can add it to this and have it stored in the log file, and it won't hurt the existing analysis tools. So this will make it easier for us to be a little more agile with adding new instrumentation sources. And then the next Darshan thing is just making sure we capture more applications that we could. One thing that I mentioned that's a little bit of a catch is that Darshan doesn't write data until you call MPI finalize. So what that means is that if you don't call MPI finalize, you're not going to get a Darshan log. This could happen for a number of reasons. This could be a bug. Could be intentional. Maybe you just don't care and didn't call MPI finalize. But more likely, you've run to the end of your job time, your wall time, and your job gets killed by the scheduler. If that happens, your job probably ran a long time, and you'd love to know what its I/O did, but we can't tell you about it right now. So we have a feature under development that'll probably be in the next Darshan release that has the ability to save a little bit more incremental data, and then if your job crashes, we can recover that data and constitute a Darshan log out of it. And the figure here is it was an interesting statistic to us. This is from the NCSA Blue Water system, they did an analysis of all their job logs and said, well, how many jobs finished successfully? And depending on which partition of the system they were looking at, the XE applications, for example, only about 61% of the jobs finished with a full successful completion code. So looking at that, that means that there's probably 39% of jobs that Darshan just didn't even have a shot at because they didn't exit cleanly and call MPI finalize. So that's the percentage of the jobs that we're trying to catch with that sort of enhancement. This has always been a vision for Darshan, but we haven't had it yet, is people are running jobs. We don't usually hear about what's going on unless they either come to a catalyst or come to support and say something's not working right, or they're doing something so incredibly terrible that systems notices. The machine's slowing down, nobody can access their files, something really bad's going on, then we go hunt down what's happening. But what would really be great is if there was more of a intelligent system that was watching these logs and flagging jobs that need attention, maybe identifying trends and things that aren't running the way they should. So we're working with two groups on that. One on mining Darshan logs and doing some interactive visualization and also trying to create some benchmarks from that. And then also we're working to integrate Darshan into a sort of bigger data collection framework. So there's information that we could likewise be getting from Lustre servers, from disk arrays, from compute nodes. The problem is, and we're part of the problem is, everyone writes a tool to look at the particular thing they're interested in. The tool we wrote looks at application I/O, and other people have written at tools that look at the disk I/O because they want optimized disk. So these tools are out there similar to Darshan, and what we need is a way to bring them together into a unified thing so that when you run your job and you run your command line utility to generate a summary, you don't just see Darshan, but you see it as part of a big picture. How busy were the servers at the time? How busy was the network? And give you a better way to do root cause analysis. So that's ongoing work. And this is just sort of a picture of how this might look. So the tools here, Darshan is something that can monitor application data on the compute nodes. IPM is a tracing tool. The burst buffer, there's data warp accounting hooks that Cray has been developing that can let you get statistics out of the burst buffer. The I/O forwarding nodes and the compute nodes can run collectd, which is something that does time series data, just kind of memory usage, proc settings, different things like that over time. And then there's a tool called LMT that can monitor Lustre. And all of these things use different file formats. They all put their data in different places. It's kind of a mess. But we've got RabbitMQ message buses here to save us. That's what I'm told. So we're going to take all this data and put it into a centralized bus that can transport the data somewhere for analysis and build a platform, likely using something like Spark and some Python that can help us get this integrated into one thing you can query. So that's the vision for the future.